All right. So yes, we are going to learn statistics, okay? And I guess just a little, I don't know, disclaimer. My method of teaching is a little old school. I'm like writing stuff on the board all the time, and we do problems on the board and things like that. I don't use PowerPoint and things like that. Although, I mean, I love technology, but some things I like old school methods, okay? And also a little disclaimer, our textbook teaches statistics from a very classical perspective, okay? So this is the statistics that people used when statistics was being founded as a subject from like the 1900s and things like that. This is a very classical approach to statistics. So I don't know if you're reading up in like the technology world and things like that, you'll hear a lot about like data mining and using big data and things like that. This class is not designed, is not meant to cover those subjects. Okay, that's this whole not a new field, but growing field of statistics known as Bayesian statistics and Monte Carlo methods and things like that. We're just kind of learning the classical side of statistics. The null hypothesis significance testing is kind of the side that it takes, which I guess more recently, I don't want to say has come under fire, but just some people are maybe shifting a little bit away from it. Okay, I guess an analogy would be, when you learn physics, you learn Newtonian physics the first time around. When you take your first physics class, you learn, force equals mass times acceleration and things like that. All of these classic Newtonian methods, but as our understanding of the world around us has gotten better, then you learn, Einstein's theory of relativity and things like that. Okay, but they always start you off with Newton and the apple falling from the tree and that kind of stuff. Okay, and the same kind of thing happens here. Okay, we're going to learn this classical approach to statistics, which I think is still great and I love it. But if you're trying to learn like the cutting edge stuff, that will come after this class, and we won't get to really cover that. Okay. All right. So why statistics? Okay. Okay. So why do we study statistics? Well, I guess with all rhetorical questions, I will answer this myself. All right, we study statistics because we want to understand the world around us, all right? And we want to make conclusions about the world based on limited data. And what I mean by limited data is this. All right? Let's say, okay, sorry. Is there a high-pitched squeal?
Yeah.
Okay. It's like spider sense is going on here. Focus. Okay. So we want to make conclusions about the world based on limited data. And what I mean by limited data is that, let's say we wanted to just answer a question like, what's the average lifespan of an American? Okay, so how long does the average American live? All right, and in order to answer this question, what do? We have to somehow look at all of the Americans. Actually, this is a very difficult question, okay? We have to look at all of the Americans that have died, I don't know, in the last year or 5 years or whatever, and we see how long they lived, okay, when they died. And then, you know, there's however hundreds of thousands or millions of people who died, we would have to, you know, take the average of all of those different people's lifespan, okay? Now, we don't have access to all of that data, okay? Yes?
Do you have, is the computer hooked up to the speakers right now? Because I think you just have to turn it off. Like,
Turn off the computer?
no, turn off the audio part.
Silencing it. I think it's just the
lights?
The lights. Sometimes the lights do that. You can play with that. And I will applaud you if you figure it out. Okay. But we don't, you know, we don't have the time to go through all of the death records that exist or whatever it is, okay? There's just too many people to answer this question. And so what we have to do is we have to look at a sample of data, okay? So maybe we look at, you know, a few different counties and we ask for their death records and things like that. And based on that, we might be able to try to come up with an estimate for this answer. Oh, look at that. Great. Thank you. And so, or anything else. You know, what if I ask, what is the height of the average American? Okay. For this, you know, there's 300-something million Americans living in the world, or living in America, and we would have to measure the height of all 300 million people, and then we would take the average of all 300 million people. Okay. Now we don't have the time or resources to gather that kind of data, so we have to work with a sample. Okay. So we work with maybe 1,000 randomly selected Americans, or maybe if we've got a lot of research money, we can survey 10,000 random Americans and try to come up with an estimate for this. Okay. But let's say we study, you know, 1,000 random Americans, and we find out that the average height of these 1,000 people is 5'7". Okay. Does that mean that the average American is 5'7"? Well, that's a nuanced question, but the answer is, well, the average height of all Americans is probably somewhat close to 5'7", but it may not necessarily be exactly 5'7". Okay, and so we're trying to make conclusions based on limited data. Okay, so the idea here is we studied a sample. Okay, I would just take it. Population represents everyone who could be interested in studying. Now, for this, for any kind of conclusions based on our sample to be valid to apply to our population, our sample needs to be representative of the population. Okay? If we are going to make conclusions based on our sample, generalize to the population, our sample needs to be representative of the population. for a sample to be representative of the population, there's a few things that we can do, but the most kind of the tool that we use would be simple random sampling. Okay, to get a representative sample, we can use simple random sampling. And we'll talk a little bit more about this later. But the idea here is that every single person in the population has an equal chance of being selected. Every single person in the population being selected. And that is simple random sampling. Now this, in theory, is a simple idea. Okay, we just say, oh, okay, we have a list of everybody and we just randomly pick people. But in practice, it's very, very, very difficult to do, because in order for every single person in the population to have an equal chance of being selected, we need to be aware of every single person in the population. We need to know who every single person in the population is, and a lot of times that's either impossible or close to impossible. Okay, so simple random sampling from a practical perspective, actually very difficult, but this serves as kind of one of our foundational assumptions for a lot of the math that we're going to do. Okay, so keep this in the back of your mind whenever we're talking about some statistical tests and things like that. Is simple random sampling a reasonable idea? Or if we're dealing with an experiment, random assignment is the other part that we can do. Okay. When we're looking at data, okay, our data can come from an observational study or an experiment. Okay. So when we look at data, our data an observational study is a study where we just do observing, okay? Where we are observers, meaning we try not to interfere with the lives of the people we're studying, okay? We observe. We try not to interfere. People or subjects that we observe. Okay. And there's like perspective or retrospective, meaning do we look at data that's been collected already, or do we come up with the idea first and then we go out and collect the data? But with an observational study, we cannot make cause and effect conclusions. Okay, no matter how good our observational study is, well, I mean, this is up to a little bit of debate. But from the classical perspective, okay, from an observational study, we cannot make cause and effect conclusions. But newspapers and people love to make cause and effect conclusions. Okay, this is the correlation fallacy. I don't know. This is just a flaw of mankind, is that we love to make cause and effect conclusions from observational studies. Okay, so we don't phrase it that way. But you know, for example, maybe somebody will do a study, and they'll say, we studied a whole bunch of people, and we noticed that people who had a glass of wine, their risk of heart disease seemed to be lower than those who didn't drink any wine. Okay. So does that mean drinking wine decreases your risk of heart disease? Okay. And the answer is no. Okay. We don't know for sure if it's the drinking of the wine that reduces heart disease, or if it's something else. Okay. There's a million things that could affect someone's heart disease. Okay. And drinking wine, we don't know if that's the reason, or if there's something else. Okay, could be something else going on associated with that. Okay, now so with drinking wine and heart disease, it seems like, well, it seems reasonable to make a cause and effect conclusion, but we can't do that. Okay, so here's a different example, and I could deal with silly examples. So another example would be, if we studied the usage of sunscreen and the prevalence of skin cancer, what we will find is that people who use more sunscreen will have higher rates of skin cancer than people who don't use sunscreen. Okay? Now, does that mean using sunscreen increases your risk of skin cancer? And the answer is no. What's going on there is that, in general, people who use sunscreen a lot go out in the sun a lot. Okay? And people who don't use sunscreen stay indoors all day. Okay, well, I mean, that's kind of this blanket statement, but there's another factor called sun exposure that drives both the rate of skin cancer and the usage of sunscreen. Okay, and so those things aren't revealed when we do an observational study. Okay, a silly example is let's say you were an alien visitor from another planet, okay, and you knew nothing about human culture or anything like that, but you can observe people, and you decide to go to a hospital, and you're just observing what's happening in the hospital. And what you notice is that sometimes you will see a man dressed in black robes holding a book, and he will enter a room with a person in bed, and he will pray or say something, and shortly after, the person in the bed dies. Okay, and you stay at the hospital for several weeks, and this seems to happen over and over and over again. Okay, it seems whenever the person in black robes with the book sits down by someone's bed and offers a prayer or something, that person dies soon after. Okay, does that mean, does that mean that the priest praying for someone causes someone to die? No. Okay, what's going on is that there's something else called just health, and when that person's health deteriorates, okay, a lot of times people will ask for kind of the death rites, these prayers to be said before someone passes, and so the deteriorating health of a patient causes the priest to come, and that causes the eventual death of the patient. Okay, but if you were an alien observer and you didn't know that, and all you just saw was that these two things happening together, you might be tempted to come to the conclusion that this man dressed in black robes is like, you know, yeah, is the Grim Reaper or something, is causing these people to die, okay? And that's not the case, all right? On the other hand, we have experiments, okay, or controlled experiments. And with an experiment, we, if possible, we try to control all of the aspects of variation that can affect the subjects that we study. Okay, we try to control you know, as many aspects of variation that we can. And what we're interested in is we're interested if wine causes an increase or decrease in heart disease. Okay, so maybe we're interested if wine increases or decreases someone's chance of heart disease, or you know, maybe we're interested if smoking causes lung cancer or something like that. Okay, so we assign our treatments to the subjects. Okay, we do not let the subjects choose which treatment they receive. And the idea here is that, you know, if we're interested if wine decreases the risk of heart disease, maybe we get 50 volunteers, okay? And so 25 people we assign to the wine group, and 25 people we assign to the no wine group, okay? Now, this is not going to happen, but if all 50 of our subjects were very willing to participate in this, we would control as many other aspects of their life as possible. We would say, you know, we would try to get all 50 people to have the same diet. We would try to get all 50 people to have the same kind of exercise routine, and we would try to get all 50 people to have, you know, the same amounts of stress or these other things that might have an impact on heart disease. Okay, we try to get these two groups to look as much alike as possible, with the exception that this group drinks wine and this group does not, okay? And so these two groups look as much alike as possible, with the exception that this one drinks wine and this one does not. And therefore, at the end of our analysis, if we notice that this group's rate of heart disease is different from this group's rate of heart disease, that difference can be attributed to the fact that one group drank wine and the other group did not, because everything else about their lives looked as similar as possible. Okay, and that's the idea behind an experiment. Okay, so the subjects don't get to choose. We try to make our groups as similar as possible. With the exception of the treatment. And then any difference between the groups can be attributed to the difference in treatments. So with a well-designed experiment, we can make cause and effect conclusions if our data support it. Any questions on this stuff so far? All right, and so the book talks about some of the kind of concepts that are used to assign treatments and things like that. Okay, because when you assign treatments, if subjects know which treatment they're receiving, that can affect the outcome because our brain is a powerful thing, and so you know, there's things like the placebo effect and whatnot. So some topics the book covers are, you know, placebo and blinding and stuff like that. Okay, and that's basically so you can give subjects some treatment without them knowing which treatment they are receiving.
I have a question.
Yes.
So, what would be the point of an observational study? Is that to give you, set you up for an experiment? I mean, if there's no.
Yeah. Okay. So you can't make
time.
cause and effect conclusions from an observational study, but you can't always do an experiment. Okay. There's ethical things that prevent us from doing all the experiments that we want to do. Okay. If and this was a problem for experiments or researchers. For a long time, researchers wanted to say, hey, smoking causes lung cancer. Okay, but you could never actually do an experiment that would determine whether smoking caused lung cancer or not. Okay, because for an experiment to work that way, we would require volunteers and would say, thank you for signing up for this study. Your cooperation is invaluable to us. And we've sorted you out into two groups at random. And group A, starting tomorrow, you guys are going to start smoking a pack of cigarettes every single day. And we're going to study, in 10 years, we're going to see how many of you have developed lung cancer. And group B, you guys are not allowed to go near any kind of cigarette smoke, and we'll see how many of you have developed lung cancer, okay? We just can't do that. There's ethical problems with that kind of experiment, okay? So, you know, we'll use mice as a stand-in, and we poison these mice with cigarette smoke, and these ones we don't, and then maybe the mice develop lung cancer, but the tobacco industry would always come back and say, well, you did the experiment on mice, but humans aren't mice, so maybe you can say smoking causes lung cancer in mice, but that doesn't say anything about humans, okay? And then you can do an observational study, and you'd say, well, we looked at all these different people, and all of these people smoked, and these people didn't smoke, and the rate of lung cancer for these people who smoked is much higher. And the tobacco industry would say, oh, well, that doesn't prove anything, okay? For all we know is that there could be a genetic condition, and these people were just predisposed to developing lung cancer anyway, okay? It was just in their genetics that they were going to develop lung cancer. And for all we know, there could be something in their genes that bother them about their lungs, and they find the smoking to be soothing, and that's why they started smoking in the first place, and they were just destined to get lung cancer anyway. Okay. Now it's a bit of a stretch argument, but it holds in terms of the logical conclusions there. So so we can't always do experiments, but observational studies do allow us to find patterns in things, okay? And so sometimes we're not always after, does this thing cause this thing, okay? If we just see, oh, you know what? People who made this purchase also tended to buy this item on Amazon.com, there's a ton of money to be made to just say, hey, people like this movie, maybe we'll put little suggested products over here because they also tend to like this thing, okay? Now, we're not saying that, if you liked, I don't know, the movie Titanic, you're going to like this other thing, and there's a cause and effect relationship, but an observational study, sometimes we're just as happy from the seeing that there's a pattern in an observational study, even if we don't know the cause and effect relationship there. Okay.
You
Yes.
mentioned perspective versus retrospective.
Uh-huh.
Can you explain that again?
Oh, okay. So when it comes to an observational study, sometimes you're going to say, sometimes you're just going to look at data that has already been gathered. Okay, so that's going to be a retrospective study.
Oh, okay.
All right.
Oh, okay.
And then other times you're going to say, hey, here's a great idea that I have, and I want to gather data for it. That's going to be a prospective study.
Okay, got it.
In terms of the analysis, that's done the same. Maybe the conclusions might be a little bit limited, or you might have to be a little bit more careful with a retrospective study because somebody else, whoever did the data collection for you, maybe they weren't looking for the same things you were. Okay. All right. Okay. So where are we going with all of this stuff? Okay. So we've talked about gathering data and all of this stuff, and we want to make conclusions from the data that we've gathered and apply it to our population, okay? Well, this is where the statistics come in, okay? And a lot of times, whenever you see course listings, they'll call statistics, or they'll also call it probability and statistics. So there's this aspect of probability that comes into play here. Okay. So let's see. All right. So let's say somebody wanted to do an experiment, and they wanted to know if exposing mice to some bacteria will increase their development of liver tumors or something like that. Okay, this is some example in the book. All right, and so what they did was they took mice, they did an experiment. And they got a total of a bunch of mice. How many mice did they get? 13 plus 49, that's 62. 62 mice, okay. So they exposed some mice to E. coli virus, and they kept other mice in a germ-free environment. For whatever reason, they put 13 mice in the E. coli environment, and 49 they kept germ-free. And then they looked after exposure. They killed all the mice, and they cut them open, and they looked at whether or not they developed liver tumors or not. Okay, and apparently a lot of mice developed liver tumors anyway. Okay, so some developed liver tumors, and then some had no tumors. All right. Of the 13 mice exposed to E. coli, 8 of them developed liver tumors, and 5 of them did not. And of the 49 mice that were kept in the germ-free environment, 19 developed liver tumors, and 30 of them did not. This was the results of our experiment. Okay, so based on this experiment, would you say, so this was an experiment, it's a controlled experiment, and the mice didn't get to have a choice on whether they were in the germ-free environment or the E. coli environment. And we kept all the other aspects as much as possible similar. Does this mean or from this, what would you say that exposure to E. coli causes an increase in the prevalence of liver tumors? Yeah, no, maybe, okay. Well, for those of you who might say yes, how would you back that up? Yeah.
Well, 8 out of 13 is a lot higher than 19 out of 49.
Okay, so we're looking at 8 out of 13 versus 19 out of 49. Okay, so in the E. coli environment, 8 out of our 13 mice, so that's about 61.5%, 0.615, about 62% of our mice developed liver tumors. And those kept in the germ-free environment, alright, there are 19 divided by 49, 0.388. Okay, about 39%. So we got 62% versus 39%. So we look at that and we say, mice exposed to E. coli, 62% of them developed liver tumors. Mice kept in a germ-free environment, only 39% developed liver tumors. Therefore, it seems that E. coli, exposure to E. coli increases the rate of liver tumors. Okay. There is that's a reasonable conclusion, okay? However, what we will learn in statistics is that we can't use this as our conclusion, okay? If I were to take there's a total of 62 mice, and 27 developed liver tumors and 35 did not, okay? If I were to take another batch of 62 mice, okay, and I split them up, 13 into an E. coli group and 49 in a germ-free group, I'm not going to get the exact same numbers here, okay? I might get a different thing, okay? And maybe I will see more mice in the E. coli group develop liver tumors, or maybe I won't, okay? And so you can imagine, all right, let's say I took 62 cards, okay? I took a deck of 62 cards, and let's just say, just for argument's sake, let's say of these 62 mice, let's say 27 of them are destined to develop liver tumors, and 35 of them will not, okay? So I've got a deck of 62 cards, 27 of them say liver tumors developed, and 35 say no tumors developed, okay? Let's say I mix these up, okay? I just shuffle these up, and I deal them out at random into two piles. One pile has 13 cards in it, and the other pile has 49 cards in it, okay? So from here, I know that there's no reason for one pile to have more or less mice with liver tumors or not, okay? This is just a result of just pure random chance. How many cards in this pile end up with liver tumors, and how many cards in this pile end up with liver tumors? Does that make sense? Okay, so I'm mixing up 62 cards, 27 of them say liver tumors, 35 of them don't. I've made two piles, one with 13 and one with 49, okay? When I flip those over, I can count how many times liver tumor shows up in this pile of 13, okay? Maybe, so let's just talk about how many we might expect to show up in that pile, okay? So right now at this point, 27 out of 62 cards, 27 divided by 62, a total of basically 43.5%. So 43.5% of these 62 cards say liver tumor on it. Okay. If I deal 13 cards, random cards into a pile, how many do I expect to say liver tumor? Well, I do 13 times 43.5%, and I'm expecting 5.67 cards, okay? 5.66 cards. So about basically 5 to 6 cards. I'm expecting about that many to just show up and say liver tumor. In the pile of 13. So if 5 cards show up with liver tumor, that doesn't seem surprising, right? If I mix it up again and I deal out 2 piles, 13 and 49, and I check the pile with 13, and 6 cards show up that say liver tumor, that also seems perfectly reasonable, right? Does it seem reasonable that 7 cards might show up that say liver tumor just by random chance? Sure, okay. Does it seem reasonable that 8 cards might show up just by random chance, by shuffling? And the answer is yes. It's not going to happen as often as 6 cards showing up that say liver tumors. But if I shuffle this and I deal cards out, sometimes I will get 8 cards that say liver tumor in the pile of 13 just by random chance. Okay? Sometimes that's going to happen. And it turns out, if we did this, if I shuffled up those 62 cards, and if I did this, 100,000 times, and I kept dealing out piles of 13 and 49, and just counting how often I get 8 cards or more show up that say liver tumors, that happens about 12% of the time. Okay? It's going to just happen purely by random chance, purely just by the fact that I'm shuffling up the cards and it's random nature. It's going to show up. I'm going to get 8 cards in this pile of 13 that say liver tumors just by random chance. Okay? Does that make sense? So, when we look at our actual data, does it seem like, okay, is it reasonable to say this could have happened just by random chance? That 27 of these mice were destined to develop liver tumors, and just by random chance, 8 of them happened to end up in my E. coli group. Does that seem reasonable? Okay, because it happens about 12% of the time just by random chance. Okay, and when we study statistics, we're going to learn probability. Okay, we're going to learn what happens when we do random shuffling. Okay, what can we expect from the random nature of things, and how often might certain events occur just by randomness. Okay, and so this could happen. This arrangement can happen 12% of the time just by random chance, and so that's not enough for us to say, you know what, E. coli is responsible for an increase in liver tumors. It might be, but at this point, with only 62 mice and this type of thing happening, we're not ready to make that conclusion. Okay, and we'll talk a little bit more about this, the thought process that goes behind these statistical tests. Okay, but this, this type of conclusion where we just look at the data and we say 8 over 13 versus 19 over 49. Okay. This worked, in high school, and it actually works in many cases. But in statistics, we're going to learn about the nature of variation and randomness, and how sometimes the data that we observe could be a result of just randomness, or it could be a result of something else at play, that maybe the E. coli actually making a difference. Okay. Yes, we have a question.
In an experiment like that,
Yes.
would it be more Would the results be more accurate if you split the total number of subjects in half instead of those arbitrary numbers?
13 and 49?
Yeah.
Would it be more accurate?
Or better, or I don't know. Those numbers seem so random.
Yeah, they are a little arbitrary, and that's just you know, whoever conducted the experiment decided to do it that way.
But would it be better to split it in half?
Yeah, probably. It would probably be better. Okay, but yeah, basically, yeah, the more you can put in each group, it's better. But yeah, I guess that's more of a design of experiments issue. Okay, and we'll talk about that very briefly. Okay. But when it comes to the analysis, sometimes you just have this data, and you gotta analyze the data that you've got. But yeah, if you could set up the experiment, it would be best to split it up evenly with 31 subjects in each group. Okay. But for all we know, maybe using E. coli required special conditions, and it was very expensive to put each mouse or rat in a E. coli environment, and therefore they could only afford to do however many. We have no idea. Okay, this just happens to be the data that we've gathered. Okay. Part of your homework tonight, or this week, or actually the next 2 weeks, is to read through chapter 1. Okay, and in section 1.1. It's going to just talk about all of these different examples, okay? And it's just it's there to, I guess, whet your appetite about for statistics. And it says, oh, here's an example. Isn't this fantastic? You're going to learn how to analyze this type of situation or example. And some of them are maybe seemingly a little bit more arbitrary than others, but they talk about how basically that's where we are headed in this class. Okay. Section 1.2 talks about the difference between observational studies and experiments, which we talked about briefly already. And 1.3 talks about samples and a population. Okay, and we again we mentioned that in brief today. Basically, the idea being that we want to make conclusions based on our data. Okay, so I think that's going to wrap up chapter 1. Please do your reading for chapter 1. Any questions that you have from there, go ahead and post onto our Facebook discussion group, or you can send me an email. We'll also take a short break, maybe about 10 minutes, and then we'll get into chapter 2.